Hey everyone, welcome back to the module. I am absolutely thrilled to be guiding you through today's explainer. We're going to be focusing on Chapter 2.2 from our text, really digging into the fundamental process activities in software engineering. If you've ever wondered how massive, complex software systems are built without just instantly collapsing into total chaos, well, you're in the right place. We're going to break down the highly structured processes that professional engineers use to turn a totally abstract idea into a fully functioning, reliable system. It's a fascinating journey from concept to code, so let's jump right in.
Here's our agenda for today. First, a welcome to software processes. Second, the 4 basic activities. Third, we'll take a deep dive into software specification. Fourth is design, implementation, and testing. Fifth, evolution and coping with change. And finally, we'll wrap up with a lecture summary and review.
All right, let's kick things off with Section 1, Welcome to Software Processes.
So, building professional software. It's not just some lone programmer hacking away at a keyboard in a basement. It takes serious structure to manage the chaos of complex systems and teams. That brings us to our core definition. A software process is an interleaved sequence of technical, collaborative, and managerial activities. And the overall goal of all this? Specifying, designing, implementing, and testing a software system. Now, a really important point the textbook highlights is that real-world processes are heavily tool-supported. Developers aren't just using basic text editors. They use a whole range of tools: requirements management systems, design model editors, program editors, automated testing tools, and debuggers. It's this incredible blend of human collaboration and advanced tooling all working together.
Moving right along to Section 2, the 4 basic activities.
No matter what you're building, there are 4 fundamental activities common to literally all software processes. First up is specification, defining what the system should actually do. Second is development, which is where we build the thing. Third is validation, checking that it actually does what the customer wants. And fourth is evolution, which is how the software changes over time. Now, here's a really common misconception. Students often think these steps have to happen in a strict one-after-the-other sequence. And while it's true that in a plan-driven waterfall model they are organized in sequence, that's definitely not the only way. In an incremental development process, these activities are interleaved. You specify a little, develop a little, validate, and then repeat. How you carry these out really depends on the type of software, the competence and experience of your developers, and the type of organization you're in.
To recap real quick, while those 4 activities, specification, development, validation, and evolution are universal, their actual arrangement is totally flexible. You'll adapt this framework based on the unique demands of your project and your team.
Let's slow down a bit for Section 3, a deep dive into software specification. Software specification, which you'll also hear called requirements engineering, is the process of understanding and defining exactly what services are required from the system, as well as identifying any constraints on its operation and development. I really want to emphasize this because the textbook is super explicit about it. This is a particularly critical stage. Why? Because mistakes made here inevitably lead to massive, expensive problems later on during system design and implementation. Seriously, if you build the wrong thing perfectly, it is still the wrong thing. But wait, before a company even starts gathering requirements, they usually carry out a feasibility study. Let's define that. It's a short-term, relatively cheap study to assess that there's actually a need or a market for the software and to figure out if it's technically and financially realistic to develop. Think about it. Before an organization drops millions of dollars on engineering, they have to check if the project makes financial sense. This study directly informs the critical business decision of whether or not to go ahead with a more detailed analysis.
Okay, so let's say the project is feasible. Now we have to document what it's going to do. But here's the catch. We can't just write one single list because different stakeholders need totally different information. We usually present requirements at 2 levels of detail. On one hand, we have user requirements. These are high-level, abstract statements made for end users and customers. They focus on what the system should do. On the other hand, we have system requirements. These are highly detailed descriptions of functionality meant specifically for system developers who need to know exactly how the system must behave. Same project, just different lenses for different audiences.
If we look at Figure 2.4, straight from our textbook, it brilliantly illustrates this entire engineering process. It maps out how information flows from our initial understanding all the way down to a final agreed-upon document. As you can see, it's not just a single step. It is an iterative cycle. Let's break these specific steps down a bit further. That diagram is built on 3 main activities:
Step 1 is requirements elicitation and analysis. This is basically the discovery phase. We figure out the system requirements by observing existing systems, having discussions with potential users and procurers, and conducting task analysis. It often involves building system models and prototypes, which are huge, because they really help you understand the system before you finalize anything. Step 2 is requirement specification. This is where we translate all that gathered information into a formal document that defines the user and system requirements. And step 3 is requirements validation. You don't just write the document and walk away. You have to check it for realism, consistency, and completeness. You'll inevitably find errors, and the document has to be modified to fix them.
So, to wrap up this deep dive, requirements engineering is all about defining what the system will do. The ultimate goal of this entire phase, from feasibility right through to validation, is producing a single, agreed-upon requirements document that satisfies the stakeholders. That document is your blueprint.
All right, let's turn to Section 4, Design, Implementation, and Testing. So, software design and implementation. This is defined as the interleaved process of actually developing an executable system for delivery to the customer. Why are they grouped together as an interleaved process? Well, design, which is the problem-solving part, and implementation, which is the actual coding, happen hand in hand. Especially if you're using an agile approach, they happen together seamlessly. Sometimes designs are formal models. Other times, they're just sketched out on whiteboards or in notebooks. But the goal is always turning that specification into a working, executable system. Once we have working code, we enter the validation phase. We have to prove the software actually meets the customer's requirements, and we do this through rigorous testing, which usually happens in stages. First, we do unit testing, which verifies that individual components work correctly on their own. Next is system or integration testing, where we stitch those units together to make sure the complete system works as a whole and there aren't any weird, unwanted interactions. Finally, we run acceptance testing. This is where we test with actual customer data to see if the software is good enough to be deployed in the real world.
So just to summarize this phase, design and implementation transform our requirements into executable code. Then through layers of software validation, unit, integration, and acceptance testing, we ensure that code actually solves the problem we set out to fix. Moving into Section 5, Evolution and Coping with Change.
Software evolution is simply the process where software is modified after its initial release. Why? Well, because the real world changes fast. New regulations pop up, competitors drop new features, and customer needs shift overnight. As the textbook points out, these changes are continuous. If your software doesn't adapt to changing market requirements, it is going to become obsolete very quickly. It has to evolve to stay useful.
Since change is literally inevitable, modern processes have to include mechanisms to cope with it. First, early prototyping. By building a quick, early version, stakeholders can play around with it. This helps anticipate required changes before you've done all the heavy lifting. Second, iterative delivery. If you deliver the system in smaller versions or increments, it's way easier to make changes without breaking the whole entire system. And third, process improvement. Good organizations constantly analyze and tweak their own internal processes to increase quality, cut costs, and speed up delivery times.
The big takeaway for this section is a massive mindset shift. Software is never truly finished. Change is just a constant, and managing that evolution through prototyping, iteration, and improving your processes is an absolutely core engineering skill.
And that brings us to Section 6, Lecture Summary and Review.
We've covered a ton of ground today. If you want to absolutely nail your exam on Chapter 2.2, here are the key facts you need to memorize. First, know those 4 universal process activities: specification, development, validation, and evolution. Second, remember that feasibility studies are cheap, early checks for technical and financial viability. Third, know the difference between user requirements, which are high-level for customers, and system requirements, which are super detailed for developers. And finally, lock in the 3 iterative steps of requirements engineering: elicitation, specification, and validation. They are the foundation of any successful project. Before we wrap up, I want to leave you with a quick question to chew on, something that connects today's foundational concepts to our next major topic. We learned today that all processes share these core activities. But if traditional plan-driven models rely on strict sequential steps and massive upfront requirements, how do these exact same activities adapt when we switch to an agile framework, where requirements might literally change on a daily basis? Think about how validation and evolution have to fundamentally shift when you're delivering new code every 2 weeks. Ponder that, because that is exactly where we're heading in our next lecture. Thank you so much for learning with me today, and I'll catch you in the next explainer.